We know that when we are talking about experimental distribution, we first of all we mean distribution of density or distribution of frequency. Okay, how often particular event occurs, or how often we can find a value equal or below given or similar. Okay, if we talk about theoretical distributions, then we talk about probabilities. So you can think about probability as a theoretical analog for the frequency. So let's discuss what probability is. Well, we will start with a very short introduction to a theory of sets, because probability relies on the theory of set. So what is a set? Set is just a collection of unique objects. You can see several sets here. For example, set A, it's a collection of three numbers, 1, 3, and 18. We have set B, which is a collection of three names. Then we have C, which is a collection of, you can think it's an outcome of flipping a coin experiment. Okay. So when we talk about objects, different objects, we can define objects using a small Latin letter. For example, in this case, I define an object which is equal to 3. 3 is a particular object. And then we can write that object belongs to a set by using this notation. So this symbol means belongs. Okay, so object X belongs to a set A. And you can see indeed that 3 is a part of set A. So indeed 3 belongs to set A. Then we can write that an object does not belong to a set using this symbol. So this symbol means does not belong to a set. So you can see that if you look at the B, you have 3 objects in B and none of them equal to 3. So apparently object 3 does not belong to a set. Okay. You can also identify an empty set. Empty set is just a set without any elements. Okay, it's like an empty box without anything. So this is how we denote the empty set. Okay. When we talk about this collection of unique objects, order doesn't matter. So it doesn't matter in which order we have the objects. And then you can think about well-known sets from mathematics. For example, integer numbers. All integer numbers, it's a set of numbers, right? So we have -2, -1, all negative numbers, and we have 0, and then we have all positive numbers. Natural numbers is only positive integer numbers, right? So we will define later a subset. You can say that the natural numbers is a subset of integer numbers. Then real numbers, it's any number can be written in decimal form. So it's a huge set of numbers. Now let's talk about two most important operations which you can do with two sets. Okay, the first operation is intersection. Intersection returns only those objects that belong to the both sets. So it means that if two sets A and B do not have common objects, the intersection will be an empty set. Let me give you some example. Let's say A has the following elements 1, 3, 5, and 7. And then B has the following elements. It's 2, 5, 3, and 8. Okay. What will be the intersection of A and B? Okay. Well, first of all, we need to find the elements that belongs both to A and B. For example, if we start with 1, apparently we don't have 1 in the B, so it will not be the result of intersection. We have 3, and 3 is in the both sets, so we have at least 3 here. Then we have 5, also we can find it in both sets, so it will be 5 here. Then 7, we don't find 7 in B. Similarly, we don't find 2 in A, and we can't find 8 in A. So that will be the intersection of the two sets A and B. Okay. The second operation, it's a union. Union is a simple thing. It's all elements together, and if we take the same A and B, let me choose a different one, so we'll have a shorter 1, 3, 5, for example, and B is 2, 3, and let's say 5 as well. Okay. So what will be the union of these two? Well, apparently we will have all elements, so we have 1, 3, 5, 2, 3, 5. But remember, set is a collection of unique objects, and so we need to use only 1, 3, and 1, 5. In this case, it will be 1, 2, 3, and 5. So that's the union of these two sets. Okay. Now let's define a subset. I already said something about subset. We can define subset as following. Subset is a set. Is a smaller set where every element is also an element of another set. For example, look at this one, A and B. Apparently, all elements in A is also an element from B. So in this case, we can say A is a subset of B. We can define a subset, or we can show that one set is a subset of another set using this notation. So this symbol means a subset. Okay. So, and this is an example. For example, if we have a subset A, which consists of 1 and 5, and subset B, which consists of 1, 3, 5, 7, 9, we can say that A is a subset of B because every element in A can be also found in B, like we see it here. Okay. And then, for example, if you take an intersection, you remember that intersection, it's objects that belong to each of these two sets. So any intersection belongs to A, and any intersection belongs to B as well. So it means that intersection of A and B is a subset of A, and intersection of A and B is also a subset of B, because all elements in intersection belongs to A and to B. Now, let's talk how we can use this theory of sets in real experiments. Okay, imagine that we have an experiment. In this case, experiment can result in different events or outcomes. So we can define a sample set is all possible outcomes of any experiment. Let me show you some examples. For example, you coin or you flip a coin. So in this case, you have only two possible outcomes. It's either you get a head or tail. So a sample set usually is denoted by omega, the Greek letter omega. As a sample set, we can write it like this. So it's all possible outcomes of this experiment, flipping a coin, tossing a coin. If you roll a die, usually you have die with 6 different numbers, 6 different elements. So it means that you will have a sample set of this experiment. So every time you're rolling a die, you will have a sample set like this. So that's all possible outcomes of this experiment. For example, if you measure a shoe size in Europe, then the smallest shoe size in Europe is 14, the largest shoe size is 49. So all these elements will be the outcome of this experiment measuring a shoe size. So it means that that's the sample set for this experiment. Okay. Now we can define another thing. It's event. Event is a subset of a sample set. So if you take any subset from these sample sets, it will be an event. For example, we flip a coin and get a head. So this is an event, and it's a subset of the sample set. So this is an event. It's a subset of the sample set. Or we roll a die and get 5. So again, we got this event, and this is a subset of the sample set. Or we measure a shoe size and get, for example, 39. So 39, it's an event of your experiment, and then it's a subset of your sample set. Okay, so sample set is simply all possible outcomes of an experiment, and event is a particular subset of a sample set.